Hello, welcome back. Today will be our 79 webinar called Making Learning-Based Visual Representation More Intelligible. Will be given by Professor José Oramas, and he will try to explain us how a black box, in this case neural networks or deep neural networks, work and are able to make predictions. This is the agenda for today. I will annoy you for 15 minutes. Then we have our presentation by Professor José Oramas, and we have the Q&A and the closing session. First of all, I want to present the DSPT. It's an informal community made by anyone that is interested in data science. We have people from the industry and the academia, and we try to make meetups where we try to share knowledge regarding the topic. Up until now, we haven't done 79 meetups and 2 international conferences. In a couple of days, will be 3 international conferences, but we'll get to that. And this is our philosophy. We want to promote knowledge between the members of the community, and we want to break barriers between the speakers and the audience. We want, at whatever level you think you are in data science, we want you to feel free to open and ask your questions and learn a little bit more. What you don't approve is selling and shameless promotion or individual or companies. This is a place to share knowledge, not to share your company or yourself. You are currently located in 5 cities, Aveiro, Braga, Coimbra, Lisboa, and Porto, and have local teams for each city. Currently, due to the pandemic, we are not doing physical meetups, and we are adopting these virtual and remote events. You can follow us in datascienceportugal.com, is our webpage. It's a little bit outdated now due to the DSPT day, but in a couple of weeks we'll be back on track. You can find job, future events, not only for this group, but other groups related with data science and another information regarding the data science community. Our presence in social media has these numbers right now. We have a strong community either in Slack, Meetup, or LinkedIn. If you want to talk with us, and talk about data science or project that you need, please follow us up in the social network. So you can join us. We need social network you prefer. And I have a special thanks for NOS for sponsoring this meetup. Before beginning with the presentation, I want to make a call for proposals. If any one of you has an interesting work or an interesting paper that it wrote regarding data science, please follow this link and talk to us so you can evaluate your work and add you as a new speaker. Next events that we are also helping is DSPT Day Online. Okay, it will be in day 17 and 18 of July. This year, the conference will be remote due to the circumstances, and it will be free. Today, I think the number of registered was 1,001, at least in the morning. So please register and guarantee your seat. We also work with other groups in data science, so we have partner events. The first one is Vision Summer School. It's a summer school related to computer vision. The DSPT Day was already presented, and LXMLX is Lisbon Machine Learning School. Is a summer school related with text mining and NLP. So you have summer schools that are useful if you want to improve your knowledge regarding image processing or NLP and text mining. I want to thank Professor José Oramas for the presentation that he is going to make. He is an assistant professor at the University of Antwerp, and he is focusing on making AI systems more intelligible. His presentation is named Making Learning-Based Visual Representations More Intelligible, and he is going to present
Okay, thank you for the introduction. Good evening. My name is José Oramas. I am part of the Internet and Data Lab from the University of Antwerp. Today, I will talk to you about how making these AI systems more intelligible. Here is an outline of what I'm going to cover in this talk. First, I will give you some intro about the topic and some context about where this research takes place. I will introduce what is model explanation and interpretation and give some motivations behind them. I will follow by giving you some details about my current research on that topic, plus some experiments that we have conducted. Later, I will draw some of the conclusions based on our results. So, before I go into more detail, let me tell you a little bit about me. In the last 10 years, I have been mostly working on the topic of computer vision. In layman terms, computer vision has the goal of giving computer systems or algorithms the sense of sight that we humans possess. And in practice, that boils down to actually recognizing and localizing objects, actions, and other information of interest in visual data. And by visual data, I mean either images or videos, right? And we can get outputs like the ones we observe in the slide right now, where we have bounding boxes for the vehicles, for the pedestrians. Perhaps we have also labels for the actions that these vehicles and pedestrians are causing. And having said that, the rest of the presentation will be focused on predictions on top of visual data, right? And how can we make this happen in practice, this localization and detection? Let's imagine that we would like to recognize a bicycle. A good way to do it is to manually define a set of features that can we use to define object parts, in this case, parts of the bike, and then define some rules that will combine these parts to form the object, right? That sounds relatively simple, but that was the main idea behind the deformable parts model proposed in 2010 by Felsens-Wolf et al. It's quite simple, yet it worked quite well back then, right? However, things have changed since 2012, as you should know, right? It's not anymore the plan to, by hand, define the set of features that the models should pay attention to. Right now, the idea is to to throw a large data set of images with the concept of interest. In this case, let's say we want to classify cats, to a deep model, in this case, a deep neural network. And the deep neural network will internally learn a representation that will correlate the prediction of interest, in this case, Siamese cats, with the input that we're taking from the data set. So the goal here is to let the model figure out what features are important. And that's what is called representation learning. In more popular terms, deep learning. So this idea of learning a representation has been quite effective in the last decade. It has matched or even surpassed human performance on some specific tasks. Therefore, we have seen in the last years a lot of headlines in the media about the successes of representation learning. So far, it looks like it's very good, that it's going along a very correct direction. However, there are some issues with it. The first one is that these models are so deep, so complex, and they are so densely interconnected that when they make a prediction, it is hard to tell what the model has actually learned internally. So it's hard to tell where inside the model specific information is encoded and what this information means. Second, when the model makes a prediction, it is hard to know what a specific part of the input, what details of the input it is taking into account when reaching a prediction, in this case, tiger cat. Throughout this presentation, I will call these problems interpretation, learning what the model has actually learned, and explanation, the task of justifying the predictions based by the model. I will focus on the problem of image classification. That is, given as input as an image, we would like to get a label that is related to some content on that image. So just keep that in mind for the rest of the presentation. So why having these insights on what the model has actually learned or why it's making a certain prediction is important. right? One of the motivations behind this, why this is desirable, is that this can help us to detect undesirable behavior that our model can have. To give an example, in the gender classification task, the researchers behind the Gender Shades project discovered that after testing several commercial gender classifiers from different companies, that the performance of these classifiers has a significant gap in performance depending on the gender and the race of the individuals. That means that if you were a Caucasian male, the classifiers would perform around 34% better than if you were a female with darker skin, which is quite a gap and may lead to unfairness later. Similarly, quite recently, you may have seen in social networks this type of images that are related with the super resolution problem, where an input that is a very low resolution image is given to a deep model. And the task of the deep model is to produce a super resolution image, like you see in the last column. Something that was observed by several researchers was that the output seemed to always converge toward features from Caucasian males, right? As you can see in these examples, we notice that, for instance, the eyes of the lady here are changed to something else, and similarly, the skin color of the lady here, or the fact that this guy doesn't have hair. So this is something undesirable. And hopefully, through model interpretation, we can get an insight on that. Similarly, we currently have in place several models that have very strong foundations, theoretical foundations behind. An example of these are the ones used for weather prediction. In the work listed below, the researchers threw a lot of weather-related data to a deep model. And the deep model was capable of matching the performance of the very principal model. However, some interesting observation that they did was that this model was using other type of information that the principal model was using. So they were, to some extent, complementary. What this means in practice? This means that for the case of the weather forecasting, being able to interpret, to know what the model has learned, can help us to discover novel factors or relationships between factors that can improve the performance of our existing model. Going back to the other case, the interpreting models or explaining the predictions of the model can help us to identify potential biases before we deploy this model into production. And it's worth noting that these biases can be caused by either the data we use to train the model or the model itself. So, what has done so far to address this problem? There has been quite some efforts in the literature. However, they have some issues. I will not go into much detail for the sake of time, but feel free to ask about that later if you are more interested. So one of the issues is that they either produce this type of visualizations for every single channel on every single layer of the network, which will require a very high amount of time for a person to inspect one by one. In the second group of work, they try to make this work more automatic by trying to match these channels, these activation channels, with a data set of pixel-wise segmentation. The problem here is that the matching will be limited by the labels on that annotated data set. And the other issue is that annotating more data is very expensive. Another issue for the case of explanation is that explanations for some algorithms, like input modification methods, could be very coarse, very pixelated, like what you see here. Explanations are usually given in the form of a heat map, in this case, very pixelated. And they are very expensive to make. The other group of work produces more fine, precise heat maps as explanations. However, the issue is that some of them are sensible to strong gradients in the data. So instead of highlighting features that justify the prediction of the model, they just highlight features that have a strong gradient. In this case, these gradients come from edges in the images. So for instance, in this case, if there is a strong edge here in the closet, the model will always highlight it independently of the prediction of the model. So that's really useless in this case. And finally, how these explanations are evaluated can depend on different things. One way is either by already making some strong assumption. For instance, if the explanation is good, it should highlight the object that is justifying. For instance, if I am predicting a dog, the explanation should highlight the dog. That makes sense for some cases. However, in this case where the goal is to know that this is a specific sheepdog, knowing that this is a sheepdog because it is a dog doesn't tell me anything extra. The second issue is that when they evaluate these explanations, is that they usually conduct a user study where they show a group of people a heat map, an explanation, and then they ask whether it makes sense compared to the explanation given, the prediction given by the model, right? The issue here is that these user studies are a bit subjective and they lend themselves to confirmation bias. That is, users will see in the heat map what they expect to see, what they want to see. So in the research I will present now, we try to address some of these issues. They don't completely solve the problem, but they try to alleviate some of these problems. So some preconditions for the work that we have done is that we will complement a pre-trained model. This will be a post hoc solution. We will assume that we have in place already a good machine learning model, a good classifier that has already been trained, and we will build an additional model that will go on top of it to provide the explanation capability. So it's an extra component. We will not modify the original model. Second, we will assume that the internal representation on that model, on that pre-trained model, is to some extent accessible. As such, this model is not a pure black box model that only takes inputs and receives outputs. So ideally, we have some access to the internals. So this makes our work more suitable when you are the developer of the method. So now going in high-level terms, what our method will do. Assuming that we have a pre-trained deep neural network that has been trained on some data covering some classes of interest, in this case, person, cat, dog, etc., we will allow interpretation of what the network has learned by generating visualizations of the relevant features from these classes, from persons, cats, and so on. So these visualizations will aim at highlighting which are the stronger features that define those objects inside the model. So how we do this in practice? In practice, we do this by passing every single image from the dataset through the model, as you see here. And we solve this optimization, where X is my data matrix that is formed by collecting all the internal activations that are produced when the image goes through the network. Depending on the computation power, we can have the activation of every single neuron in the architecture, or we can produce only channel-wise activations. So we can significantly reduce the number of points that each of my feature vectors will have. In addition, we will have this L term which corresponds to the label predicted by the model. In this case, tiger cat. Then the goal is to learn which is the optimal weight matrix W that will give a stronger weights to the features that are more relevant to link the input with the given prediction. However, something to keep in mind is that even when we focus on this path that produces the prediction, the number of neurons involved on that path could be still quite high, probably a few hundreds. For that reason, if we make visualizations from all these features, we may saturate the person looking at the visualizations. For this reason, we will introduce some sparsity there, and we will focus on the most relevant features on that path that lead to the decision. And we do that by imposing this constraint here. This optimization is addressed using the formulated as a mu lasso problem, which is quite optimal, because in this case, each of the internal activations of the X matrix will be very, very high dimensional. Depending on the architectures, this could be on the 100,000s or millions. So this will be a very horizontal matrix, and that's the optimal case where mu lasso operates. Moreover, if we have multiple classes, we can parallelize this optimization in different computers, each one handling one class at a time. So it lends itself for very good optimizations. With this in place, for each class of interest, we will know which layer and which channel on that layer is relevant for the class. So with that information, we can go to specific, for every feature, we will go to the layer and channel where that feature is located and produce an activation map like you see here. What we do next is looking for the activation with the part in the activation map with the highest response. In this case, the tip of the nose of the cat. Then, using the information of the architecture, we can know what is the receptive field on that specific channel and layer, which in this case is represented by the square. Using that information, we go back to the input image and define the very same region. We'll repeat this process for all the images of this class, in this case cat, for that specific feature. And we produce an average of all those cropped regions. And we obtain a visualization like this. In this case, the interpretation visualization is telling me that some feature very related to the nose of the cat is important for this class. Following the same procedure for different classes and different relevant features, we can obtain visualizations like the ones you see here, right? Here is a subset of classes from the 1,000 categories from the ImageNet dataset, covering different objects, animals, and scene types. So in some cases, you can see like a balloon, you can see again like a golden retriever, some birds here from far and from close, and so on. So this is how our interpretations visualizations will look like. Now that we know the relevant features from every class of interest, we will do explanation. First, once we give as input an image to the model, we will obtain a prediction. That is what you see marked there. Then for each of the predicted classes, we will look between the set of relevant features, which are the ones who have the strongest response on those specific inputs. And for each of them, we will generate a heat map. In this case, these heat maps will be my explanation. Each explanation will highlight a different feature. For instance, in the case of a tiger, the model thinks it is a tiger because of the pattern around the eyes, the mustache, and some fur around the nose. And similarly, for the case of tiger cat here in the bottom. Right? So this is how we will explain our predictions. Now, how did we evaluate this model? We conduct experiments on 4 datasets: MNIST, which is a traditional digit dataset with 10 classes, the 1,000 classes from ImageNet dataset. Then we have also a subset of 13 classes, which we call ImageNet cats, which focus on cats and felines from the dataset. And finally, we cover the Fashion 144K dataset, which has the images from social networks and 12 classes in total. The images look like the one you see on your right. The first experiment we do is we verify how important these selected relevant features really are. And the assumption here is that if they are relevant, they are very important for the classes. The moment we remove them, the model should suffer a drop in performance. So in order to verify this, what we plot here for the 4 datasets in dark red is the original performance of the model. And performance is reported in terms of mean classification accuracy. In orange, you see what the performance will be if we only select relevant features from the fully connected layers in the model. in blue, in light blue, is the performance if we select the features from the entire architecture. So something that we can notice directly is that whenever we do this selection, there's a significant drop in performance, which suggests that indeed the features we are identifying are important to make the classifications for the model. In the second part of the evaluation, I will show some qualitative results on the visual interpretation. Here you see some results on the ImageNet CATS dataset. Something interesting to see is that some of the features we are identifying are related to the nose of the cat. Some others seem to be related to patterns in their fur. And we can see others related with colors and maybe environment where they are located. For the case of the Fashion 144K dataset, we focus on the human-centered geolocation task, where the goal is, given one of these images, we would like to predict in which of 12 different locations the photo was actually taken. After running our interpretation algorithm on this classifier, we had the following interpretation visualizations. Some patterns we observed is that in cities like LA and Miami, relevant features seem to look like naked legs. This to some extent makes sense because in those cities, temperature is a bit higher and probably people wear more skirts and shorts. On the contrary, we saw an opposite trend in London, Montreal, and Paris, where the features seem to be more like long covered legs, right? Probably because sometimes it's colder there in comparison. And we see similar behaviors for other cities, like Melbourne, where there is a lot of vegetation and the color green seem to be present, and in North Europe, where we see a lot of white and black contrasts, and also it's common to see people wearing in dark behind a white background. Regarding visual explanation, here I show some qualitative examples of on the MNIST and Fashion 144K dataset. Some interesting observations to make here is that our model, for instance, in this number 8, highlight features that should be present in order to avoid confusion with another class. For instance, if the highlighted regions in the number 8 were missing, probably this number will be confused with a number 3. On the contrary, our model also seems to highlight features that must be absent to also avoid confusion. In this case, we are looking at the example of this number 5. Something interesting is that we see this little piece of the number 5 that is highlighted here, that is actually highlighted an empty space in the input, which means that that little piece should be missing, probably because if that little piece was in place, this number 5 will now look like a number 6, and the model will make an error. Now, I show you some visualizations, some explanations, some heat maps, but really how good these heat maps are. So far, as I told you already, this has been evaluated in different forms, which might not be so objective, right? Here, in order to have an objective evaluation of these explanations, we propose the use of a synthetic dataset where we control the discriminative feature by design. For instance, in this case, we have this eggplant where the egg on top, the color of the egg, defines the class of interest. In this case, we have 6 classes. We can do something similar if we change the color of the part in the bottom and produce a similar dataset, but now with 12. The idea is that if the color part is the relevant part, the relevant feature that defines the class, this is the part that should be highlighted by the heat map. So, since this is a synthetic dataset, we can generate these ground truth masks that indicate where the colorful part is located. And we can use this to measure the overlap with the heat map. So here are some qualitative results where you see the input, the corresponding ground truth masks, and then in every column you see different explanations, different heat maps from different methods in the literature. In summary, our method, which is in the last column, seems to have a very good trade-off between covering large regions, like the top of the eggplant in the second figure, avoiding any overlapping. Similarly, it's able to highlight very small regions to a decent extent. As I said before, we can measure quantitatively how good this overlap of the heat map is with respect to the ground truth masks. In this case, back then, our method was the top performing one with the ones in the literature. In addition, to complement this experiment, we run our interpretation method on top of the classifier used for this eggplant. And we observe the following. On the first row, you can see some examples of the input of the classes considered by the classifier. In the bottom, you see some of the relevant features. As you can notice, our method is able to not only identify the color that is relevant for the class, but also the part that should have it. For instance, in the second column, we notice that the color blue, the big block, is telling us that blue is important, and above it, we see the part of the eggplant that should have it. So this, to some extent, matches the original hypothesis we had and shows that the interpretation method is capable of identifying the features that are important for the model and the classes of interests. So to conclude, I have presented you a method to do visual interpretation through visualizations of relevant features. I have also shown you how to do visual explanation by verifying the response of these relevant features on a very specific input. And finally, I have shown you an objective evaluation protocol to assess how good these explanations, these heat maps, really are. Something to keep in mind is that at this point, I am covering a very specific case with this synthetic dataset. So depending on the nature of the problem handled by the classifier, we will need to extend this synthetic example to cover more scenarios that may be handled by our classifier. So the take-home message after presenting all this is that AI-related technologies have improved significantly, as I said at the beginning. However, it is far from being perfect. That's why we need to have all these extra steps to do model interpretation, to provide explanation to our users. And there is also some sanity checks that we can do that are presented in the literature that we can do in order to ensure that our model is doing what it's supposed to do. Some acknowledgements about this research, of course. This effort is not my only work. There is a nice team of collaborators behind this. In this case, my master's student, Kylie Wan, and Professor Tine Teutelars from the KU Leuven. Having said that, thank you for your attention, and I will be glad to answer any questions that you may have.
Thank you for your nice presentation. We have a couple of questions here. I didn't explain, but please feel free to write your questions in the YouTube chat, and we'll copy them to our streaming platform. The question will be showed as a banner, and I will talk with José for a reply. So the first question that we have is this one. I will show it. Unit testing for machine learning. Do you believe your method can be used as unit testing for validation of a method?
Well, to some extent, it is possible. You can validate. The idea of this method is to really give the user a really good idea of what is going on. Not just really the user, but also the developers, because it can be also used as a debugging tool. Right? It can be used. However, depending on the problem, there are many aspects that should be evaluated for the method. So what I am proposing right now has some specific aspects that is addressing, but not all of them. So it really will depend on the problem that you have at hand. Right now, we have a general solution, but because of its generality, it may not address specific details that some problems may have. So it could be used, but it's not a definitive solution for machine learning, I would say.
Okay, is it ongoing research? I think is in the same alley that the previous question. This explanation needs to be validated by a human.
Well, there are two. I would say there are two answers to these questions. I would say, if you are, let's say, if you are using this tool as a developer, right, as a debugging tool to verify how good your method perform, then yes, then this explanation is supposed to fit the human, in this case the developer, with what's going on in the model, so it can be improved. So if the developer can indeed verify how good this is, he can fix any problem that might be, or bias that is present in the model before it goes into production. In the second case, where this model is already put into production, right? The idea of this explanation of these explanations is to give some feeling, some idea of what the model is taking into account when giving a prediction. For instance, why my loan was rejected, why my face gets detected, why I get these suggestions by some recommendation system, right? Per se, they don't need to be very detailed like the ones given to the developer. So in this case, they don't really need to be 100% validated, but they need to be relatively friendly and approachable to the end user. Otherwise, the explanation will not satisfy their goal of serving humans.
A follow-up question, sorry. Do you think this method, if properly researched, could be used without the input of a human? Do you imagine a situation that you can have a data set to evaluate the bias of a model trained in another data set? Does it matter?
Well, maybe if there is a bias, let's assume we are in this scenario where there is a bias in the model, right? If there is a bias in the model, what I will expect is that all these average visualizations that we observe, they will show a similar picture, right? If so, then you can have some perceptual metric between all of them. And that can show you that all these visualizations that are supposed to cover diverse features are all collapsing into a single feature, having a very close similarity. I guess for that specific problem, there is a way to do it. However, we need to make sure that before giving this task to a machine, that we can formally define all the problems that could be in place, right? Because if we can formally define, then we can have, let's say, an automatic way of addressing them, like I just described with the mode collapse issue. So there might be a possibility, but I think formally defining all these possible problems might be more difficult.
Thank you. Following, can this model be used as a constraint factor in an optimization algorithm? Well, I guess it depends on what you would like to optimize. So, for instance, taking as a starting point the example I just gave before, right? If your optimization is towards having a diverse representation internally, right? You can put a loss that will measure the difference between the representation encoded by these interpretation visualizations, right? As long as the distance between them is significantly high, you can ensure that your algorithm is looking for diverse, let's say, fitting onto diverse features. If not, it may indicate that it's collapsing. So it can be used. However,
I guess it will depend a lot on the optimization, on what you're optimizing for. Yes, I think that will be my answer there.
Thank you. I imagine that the idea was to reduce bias or certain bias in the model. Can this be a constraint to reduce certain bias? So I want to limit certain pixels or certain parts of the image, because I know that for example, in your example, he detected cat not by the cat features, but by the outside where the cat was. So can I use it as please don't consider this part of the image?
Well,
try to learn.
Well, the thing there is that I guess you can use it, but the issue there is that normally, going back to the beginning of the presentation, right? The idea, in theory, the idea is that the model will figure out what are the patterns in the data. For the case of the cat, it's possible that, well, in this case, the reason why that happened is because this is a domestic cat. And apparently, a lot of the pictures in the dataset were taken in backyards or in parks, so there was always vegetation, right? However, there are some categories where the context is still a relevant feature. So really may depend on what the class of interest, what the concept that you're modeling behaves, what are the relevant information there. In order to, going back to your example, whether you can use this method to really constrain what are the regions of interest, I guess you can use these heat maps to really mark where are the regions that you would like your model to focus. However, I'm not so sure. I mean, there might be specific applications where this is of interest, where this is applicable. But I would say in the general representation learning context, where the idea is to let the model figure out what is relevant, it might not have a good place, I believe.
My idea was not regarding cats, but regarding color or race or gender of humans. So in that case, I don't want him to understand that I'm a Caucasian man, so I have a societal benefit. I don't want him to learn this type of bias. Although they exist, I want to minimize this type of bias in the model.
Well, I guess you can do it if you have a formal way to, let's say, in this case, you're talking about skin color, right? If there is a formal way to match the feature, let's say, the concept, the skin color, to the relevant feature that is detected. If you can do that connection, then yes, you can use this to penalize, let's say, concepts that are being identified as relevant. So for instance, if something like shape of the eyes or skin color is something you would like to avoid, you need to penalize links between those concepts with the identified relevant features. So this way, those could be removed from the model.
That is interesting, and I think it's helpful in this when there are models that learn bias from the society. Do we have an open source implementation that you can try by yourselves?
Yeah, well, that's a good question. We have some code. We still have to hang it. We have the website. There is if you type my name or you send me an email, I will send you the link. We have a website for that project, and there is some code. Well, there's some code that we still have to put in there. We have an implementation that we can make available. I think it's possible that we can do. It's not online yet, but we hope to have it as soon as possible. That's from the method I presented. From other methods that are listed on the paper, also if you type my name, you will find the paper that is related to this work. You will find that I make citations to other work that are related to explanations, to how to generate these heat maps and so on. And from some of those, there is already code online that you can try.
Anyone that is interested, please send an email to José at the end, and he'll share at least the code that he has right now. Thank you for that. Currently, a lot of people talk about performance-based explainability as a trade-off. Do you agree with this mindset?
Yeah, well, I do agree. I do agree with the fact that if we have something that works very good, we should not sacrifice that performance just for the sake of making explainable. That's why we, for instance, in this work, we try to come with a post hoc solution that will not touch the original model, will just complement it and extend its output with the explanations, right? There is another line of research that is also interesting, that is about designing models with what they call built-in interpretability, or which are explainable by design. So, and the goal of those is to to produce a model that is as good as the original model, the base model, with the properties that its internal representation is to some extent disentangled, separated. So you can really identify where specific features are encoded. So there is quite some research going on along that direction. And personally, I have some students trying to also move a bit on that way. But I think indeed, if we have something that works very good, it's not such a good idea to sacrifice performance just for the sake of explainability. On the other hand, if this model is making decisions that are affecting people, then I think that sacrifice might be worth.
So you understand that the model should learn the pattern that it wants, and we try to use the pattern that he learned.
Well, not just a pattern, but actually it will learn. It will internal. Let's say usually what you have is that features in the representation are entangled. For instance, in some parts you may have like blue car. If we are talking about cars, you may have blue cars, red cars, white cars, and so on, right? Something that can happen is that in a disentangled model is that the representation is splitted, where one part focuses on shapes, like different shapes that a car can have, and another part will focus on different colors that the car can have. So depending how the model activates, you know which, let's say, combination of this type of features is present on the data. So this way, let's say you are not telling the model, I want shapes and colors. The model learns that itself, right? Yet it achieves good performance. Yet, because it's separated, disentangled, it is easy to understand what different parts of the representation mean.
Okay, thank you. Moving to the last two questions right now. If you have some other question, this is for the audience, please write them on the chat so you can ask them now. Does the explanation model works with other MEL models?
Yeah. Maybe if I go back, let me go several slides back.
Your slides are not showing now, but I will ask Rui, please show the slides.
Then, yeah, that will give me time when I go all the way back. Okay, so I guess this is an important slide. Yeah, as I said before, right? This is about matching how the model reacts internally, the blue line, with respect to the prediction of the model. It's about finding that relationship between the internal activation, the internal state, and the predicted label. If we have another model, machine learning model, like a decision tree, a SVM, a conditional random field, that will provide us this insight about the internal state, right? We can also do that mapping there, right? In this case, if you focus on the equation below, that's independent of what the model we are evaluating, where we're obtaining, the features X and the predictions L. So yes, it can be applicable as long as we have some access to the internal state of the model. So we can learn this relationship.
Does this method work with other datasets to an image? I think you already mentioned it.
Well, I need to go to that one. That's a very good question, and the answer is not really, right? Especially if you look into this in this image that you see here, right? The interpretation visualization, which is an average. For the case of image, we have this 2D matrix where we do this average operation. And the result is still observable, right? And we can get this ghost blurry image that displays the feature. For instance, if this was audio, it is averaging audio signals is a bit more complicated. If these signals are not properly aligned, the output that we will get as an average will not be, let's say, understandable by us, will not be perceptible. So in that situation, we may get a problem. So it might be possible, but we may need a good operation to do the combination, right? In this case, for the images, an average works. That's sufficient. But for the case of audio, that might not be enough. So that's something to keep in mind.
Okay, thank you. So you have to have a new student work on this, because
Yes.
I think a lot of data sets will be table-based with a lot of values, and
Yes.
it will be interesting to have a tree-like explanation for the output.
Yeah.
And for time series, especially.
Yeah, well, for time series, if it's explanation, you can highlight, let's say, which elements in the time series are relevant, and maybe go more, let's say, into the features of that element, right? We have already some research with some students on time series data, but for the case of explanation, but for the case of the interpretation, where this average operation is needed, that really depends a lot on the nature of the data. I think for time series, even if it's images like videos, we will still be able to do this. For the case of audio, is where it becomes a bit more challenging. For instance, for the case of text, it's possible that we can use a dictionary to figure out that some of these texts, some of these words are actually synonyms, and we can disambiguate all of them and group them properly. But let's say this step where the combination of the features is conducted might depend on the nature of the data, on the modality.
I would thought that time series, due to the loop inherent in the neural network, would be quite tricky to represent.
Well, if it's
I thought in a long-term short memory.
Sorry?
I thought on an LSTM. Yes.
No, it's possible, because let's say you have indeed these cycles, right?
Yes.
But these cycles are taken after observing every single, let's say, example which come from a different timestamp. So you can do a similar procedure every time an example is observed. And your heat maps, let's say, it would be like a hierarchy. The first one telling you which example, which element in the timestamps is relevant, and you can go one level deeper, and which features of that element are the ones that actually make it relevant. So it's possible, but again, I think the challenge is that if you want to do interpretation, might be related to how you combine the different features from the type of data.
It becomes trickier as you leave the image part. And this is the last question that you have right now. Would you use this at the beginning of the project to make decision on which pre-trained model to use?
Well, I guess it will be good as a type of sanity check if you want to be sure that the model you will use has no internal bias, right? Because you run this, you get these groups of visualizations, and then you can verify whether, for instance, for the case of orange, whether they are, or this robin bird, they are all focusing on the very same thing. For instance, if this was, let's assume this was a face detector, and all our features are highlighting something that looks like a Caucasian male, that will already tell us that it's a bad idea to use this, because maybe for females or for people from another skin color, it will not work properly. So it could be a good idea if you want to identify these things.
Thank you. Do you think that the pre-trained model bias or initial performance validated by your interpretable model does change a lot or doesn't change much after being trained in the proper data set? The initial step, is that really important for the final?
But I didn't understand the question.
Imagine that you have a pre-trained model and you validate with your method, and it apparently doesn't have a lot of bias. Do you think after training in a proper data set for the scenario, the condition of not having bias still maintains, or will be added by the data set that you use to refine the pre-trained model?
Well, but I guess it really depends how you define bias, right? Because normally what these models do is that they will just identify the pattern that is frequent on your data and exploit it to make predictions. If your model has a bias like the one you mentioned, like related with skin color, I mean, the model is operating properly, but that's not desirable. So let's assume you fix it, right, with a new data set. If you fix it by changing the data, that means that your data doesn't have that bias anymore. And when you do the interpretation, that should be reflected there as well. Normally, if your data is indeed unbiased, you will see that in practice, your model should generalize properly, because it will not only work for one specific gender or race and so on.
Okay, I think I understand. Thank you for all your replies. I think the audience is satisfied with the answers. Correct me if I'm wrong, but one of the takeaways here is that the model don't see bias as humans. He just sees patterns to explore and detect. And sanity validation tools as the one that you produce are necessary, even more than previously, to guarantee that your model is stable.
Yes, I agree with that. I mean, they exploit patterns, but those patterns are not necessarily desirable, like the ones we described. And that's why we need some of these things. In some cases, that might not be a problem, but in some others where people is involved, where this can have an impact on people, or can not just have an impact, but it can also become like an echo chamber, where it will actually extend the effect of a given bias, then this is really undesirable, and hence the need for this type of tools.
Thank you for the replies. I want to thank you for your talk. It was very interesting and very complete and deep regarding the topic. Thank you for being in this meetup.
Thanks a lot for having me.
It's our pleasure. We hope to have you again when you have another, when you fix some of these issues that we talked about today.
Sure.
And I have a couple of slides to finish this meetup. Again, I want to make a call for proposals. If you yourself has an interesting work in data science, or do you know a colleague, a friend that has done something worthwhile in data science, either data collection, data cleaning, modeling, optimization algorithms, whatever you think that is interesting for the topic, follow this link and contact us, so we'll evaluate your effort and put it as a speaker for a following event. I want to ask you all to go to this link and fill up the survey. We need a lot of replies from you to be able to improve our remote meetups. They are not at the same interoperability level as the physical ones. We are trying to improve that. This is the fourth one, the fourth remote meetup, and I think it's the fourth time we have a different Q&A system. We are trying to make them more interpretable for you, but please fill up the survey so we know what works for you, what doesn't work, and what have to work in these remote events to make it better for your experience. And this is all for me. I hope you liked the meetup, and I hope to see you again soon.